On the quiet morning of January 16, 1943, an ominous event unfolded as the SS Schenectady, a newly commissioned Liberty ship, lay moored peacefully at its dock in Portland, Oregon. This vessel, a mere 10 weeks old and freshly constructed from the bustling Kaiser shipyards, was not subjected to the perils of enemy engagement or the tumultuous wrath of a violent tempest. The harbor waters remained placid, reflecting the calm of the day. Suddenly, a sharp, resounding crack reverberated across the tranquil expanse, and within moments, the entire ship catastrophically fractured into two distinct sections. Its robust hull cleaved from its uppermost deck to its very keel, as if sundered by an unseen, razor-sharp force. The crew members, caught entirely by surprise, scrambled desperately as the bow and stern sections sagged dramatically in opposing directions, the ship's structural integrity utterly compromised while it was ostensibly safe at its berth. The plight of the Schenectady was not an isolated incident. During that same harsh winter, the SS John P. Gaines similarly succumbed, breaking apart inexplicably in calm waters. The SS Manhattan, a T-2 tanker fabricated using identical construction methodologies, suffered such severe cracking that its terrified crew were compelled to abandon ship in a state of panic. Over the course of 1943 and 1944, a staggering total exceeding 2,500 Liberty ships reported critical structural anomalies, including extensive hull cracks, deck fractures, and outright catastrophic splits. A minimum of 19 of these vessels completely disintegrated into two pieces. Even more chillingly, 3 ships vanished without a trace at sea, disintegrating with such alarming rapidity that they were unable to transmit even a rudimentary distress signal. These were not the grim statistics of wartime casualties. Rather, these were ships inexplicably succumbing to what appeared to be self-destruction. The United States had staked its entire strategic fortunes on the ambitious Liberty ship program. Following the devastating attack on Pearl Harbor, which plunged America into the maelstrom of total war, the nation faced an urgent and critical demand for cargo vessels, hundreds of them, and with extreme expediency. Conventional shipbuilding processes typically necessitated 8 arduous months for the completion of a single vessel. The Maritime Commission, facing an existential crisis, simply could not afford such protracted timelines. It was at this juncture that Henry Kaiser, an audacious industrialist with no prior experience in maritime construction, presented a truly revolutionary proposition: the mass production of freighters, akin to the assembly line manufacturing of automobiles, capable of rolling off production lines in a matter of weeks rather than months. His sprawling Richmond, California, shipyards pioneered groundbreaking techniques. Arc welding replaced traditional riveting, prefabricated sections superseded tedious piece-by-piece construction, and the logistical efficiencies of assembly lines were ingeniously borrowed from Detroit's automotive factories. By the latter half of 1942, Kaiser's highly efficient yards were achieving an astonishing feat, launching Liberty ships in an average of just 42 days. The powerful propaganda machinery of the era enthusiastically lauded this industrial marvel. Newsreels showcased the iconic Rosie the Riveters, though, in this new manufacturing paradigm, they were predominantly skilled welders, transforming massive steel plates into formidable seagoing vessels at what seemed like impossible velocities. The SS Robert E. Peary established an unprecedented record in November 1942, being constructed from the laying of its keel to its launch in an astonishing 4 days and 15 hours. Americans universally cheered this display of industrial might. The Allied shipping tonnage, which had been brutally decimated by relentless U-boat wolf packs, was finally receiving a desperately needed influx of reinforcements pouring into the treacherous waters of the Atlantic. However, a deeply disturbing pattern soon emerged. These ships began to fail, not from the expected ravages of torpedo damage or the stresses of tempestuous seas, but spontaneously and catastrophically, under conditions that should have been entirely routine. Naval architects found themselves utterly perplexed. The welds appeared structurally sound. The steel materials meticulously conformed to all specified requirements. The fundamental designs were derived from proven and reliable British blueprints. Yet, despite these assurances, Liberty ships were fracturing with the fragility of delicate porcelain teacups. The cracks typically originated at points of acute stress concentration, the sharp corners of hatch openings, the bases of gun mounts, and the inherently squared-off design elements of the hull. Once a crack initiated, it would propagate through the welded hull plates with terrifying velocity, sometimes traversing the entire length of a vessel in a matter of mere seconds. In response to this escalating crisis, the Maritime Commission promptly convened emergency investigations. Metallurgists meticulously examined failed sections of steel under powerful microscopes. Engineers exhaustively reviewed intricate stress calculations. Naval inspectors painstakingly crawled through the compromised hulls, equipped with precision measuring instruments. Every expert sought the elusive culprit. Was it inferior steel, flawed welds, inherent design deficiencies, or inadequate quality control? Meanwhile, ships continued to split apart while committees engaged in fervent debate. Sailors became increasingly gripped by a profound fear of their own vessels, haunted by the chilling knowledge that the hull beneath their feet might unpredictably unzip without warning in the frigid, unforgiving waters of the Atlantic. The celebrated miracle of mass production had, in a shockingly short span, devolved into a maritime nightmare, and no one possessed a clear explanation as to why ships built in record time were failing in record numbers. The definitive answer to this perplexing conundrum emerged from the most improbable of sources: a welder working diligently on the assembly line, a person whose role typically did not involve questioning high-level engineering decisions. Bessie Hamill worked the demanding graveyard shift at Kaiser's Richmond Yard No. 3, one of countless women who had bravely entered the demanding world of shipyard labor after men were deployed overseas. She had been welding substantial hull sections for 8 months, a period sufficiently long to observe something that the highly educated engineers had apparently overlooked. Every night, she witnessed her team meticulously welding massive steel plates in a sequence that, from a mechanical perspective, made absolutely no rational sense. Hamill observed welders commencing their work at the edges of plates and proceeding inward, or initiating a long seam at one end and running a continuous bead straight to the other. As each weld cooled, the metal inevitably contracted, exerting immense pulling and warping forces on the plates. She could visually discern the accumulating stress, watching the steel visibly distort beneath the intense heat of her torch. When welders completed one section and moved to the next, they were, in effect, permanently embedding and locking that residual stress into the structural integrity of the ship. It was analogous to tightening the central bolts on a car wheel before securing the outer ones, a surefire recipe for inherent imbalance and eventual failure. Her foreman, a figure of authority, summarily dismissed her concerns. She was, after all, merely a welder, not a degreed engineer. The prescribed welding sequence, he asserted, originated directly from the engineering department, from men possessing advanced college degrees and specialized naval architecture training. Undeterred, Hamill persisted. In November 1943, she boldly requested a meeting with yard supervisors, an act that flagrantly violated established chain of command protocols, and could have easily resulted in her immediate termination. She arrived prepared, bringing tangible evidence, test plates she had personally welded on her own time, experimenting with different sequences. Some of these samples clearly exhibited significant warping and unmistakable stress patterns. Others, however, which she had meticulously welded from the center outward in a carefully planned sequence, lay perfectly flat and true, displaying minimal distortion. The supervisors, initially skeptical of a welder's unconventional insights, were nonetheless intrigued by her compelling demonstration. One supervisor ultimately agreed to personally observe the production line during Hamel's shift. What he witnessed unequivocally confirmed her astute observations. Welders were, in essence, systematically torturing the steel, forcing it to absorb and retain internal stresses that it would carry throughout its entire operational life. Every cooling weld generated residual tensile stress permanently embedded within the metal. The existing construction sequence meant that these internal stresses accumulated and concentrated at highly specific points, particularly at the sharp corners of hatch openings and other well-known stress concentration areas. When these ships subsequently encountered the brutally cold waters of the North Atlantic, the steel itself became dangerously brittle. The combination of locked and residual stress and this newfound brittleness created the perfect, catastrophic conditions for sudden, catastrophic fracture. Hamel's profound insight was elegantly simple yet remarkably effective. Welders should commence their work from the center of sections and proceed outward, thereby allowing stress to dissipate harmlessly toward the edges rather than concentrating perilously in the middle. Furthermore, she advocated for alternating welding locations to prevent an excessive buildup of heat in any single area. Crucially, she advised against completing welds in long, continuous runs. Instead, she proposed the implementation of a balanced, staggered sequence that meticulously distributed cooling stresses evenly across the entire structure. These were not groundbreaking metallurgical theories derived from advanced scientific principles. Rather, they were practical, empirical observations gleaned from someone who intimately worked with the material every single day, someone who felt the subtle movements of the metal beneath her torch and instinctively recognized the profound consequences of improper technique. By December 1943, Bessie Hamel's crucial observations had ascended the corporate ladder, eventually reaching the esteemed Henry Kaiser himself. He was confronted with a brutal and politically charged choice. The vaunted Liberty ship program was already under intense congressional scrutiny due to the alarming epidemic of cracking. Admitting that the fundamental problem lay not with the quality of the steel or the integrity of the welds, but rather with the very construction sequence itself, meant acknowledging that every single ship built to date contained systematic flaws inherently baked into their hulls. It necessitated a temporary but significant slowdown in production to thoroughly retrain thousands of welders. It also demanded a complete redesign of the entire assembly process. However, it also presented the tantalizing possibility of definitively resolving the catastrophic fracture crisis that threatened to utterly undermine America's entire maritime logistics chain, a critical component of the war effort. Kaiser, to his immense credit and demonstrating remarkable foresight, did not hesitate. He promptly authorized immediate and extensive testing of Hamel's theories, going so far as to pull an entire hull section from the active production line for experimental reconstruction. The very metallurgists and engineers who had spent months meticulously analyzing the failed ships were now, remarkably, taking direct instruction from a night shift welder who had never once stepped foot inside a college classroom. The subsequent test results were both damning and revelatory in equal measure. When Kaiser's metallurgists meticulously examined hull sections constructed using conventional sequences versus those built using Hamel's innovative methods, the difference was both precisely measurable and dramatically evident. Residual stress gauges revealed that traditionally welded sections carried internal tensions exceeding an astonishing 30,000 pounds per square inch, intensely concentrated at critical structural points. Conversely, Hamill's meticulously sequenced sections effectively distributed those stresses across much broader areas, with peak readings barely reaching 12,000 psi. The steel material itself was absolutely identical. The welds were chemically indistinguishable. Only the precise order of operations had been altered, yet the structural integrity of the ships had improved by factors that the engineers initially found difficult to believe. The intricate physics underlying these catastrophic failures finally became unequivocally clear. Steel is not a passive, static material. It is a dynamic crystalline structure that responds profoundly to changes in temperature. When welders guide a torch along a seam, they generate a highly localized temperature exceeding a blistering 2,500 degrees Fahrenheit. The metal within that intensely hot zone expands dramatically. As the weld subsequently cools, it contracts, but the surrounding, colder steel rigidly constrains that contraction. The inevitable result is residual tensile stress, which becomes permanently locked into the structure unless the welding sequence is specifically designed to allow this stress to effectively redistribute. Liberty ships were suffering from what metallurgists precisely term brittle fracture propagation. The specific type of steel utilized in their hulls, a carbon steel designated as shipbuilding grade, performed adequately in warmer waters. However, it underwent a critical and dangerous transformation in the near-freezing temperatures of the North Atlantic. Below approximately 40 degrees Fahrenheit, the steel's inherent ductility, its ability to deform without breaking, collapsed precipitously. Under normal conditions, metal absorbs stress by deforming slightly, bending rather than fracturing. Cold steel, however, loses this vital flexibility. It becomes alarmingly brittle, behaving more like fragile glass than the tough, resilient material that welders skillfully manipulated in California's mild shipyards. When unyielding steel encounters intense internal strain at an acute angle, for instance, the precise, rectilinear perimeter of a cargo hatchway, the immutable laws of physics assert their dominance with devastating efficacy. A minuscule fissure invariably begins to form. Within the confines of a more malleable, ductile steel, such a nascent crack would typically cease its progression, its destructive potential absorbed by the material's inherent capacity to deform and stretch. However, in rigid, brittle steel subjected to pulling forces, this incipient flaw rapidly transforms into an unstoppable, accelerating fracture. The latent potential energy embedded within these persistent internal stresses provides the irresistible impetus for the crack's relentless expansion. Acute angles function as potent focal points for stress, amplifying the localized strain by magnitudes of 3 or even greater. The fissure then gains incredible momentum, occasionally surpassing the velocity of sound waves propagating through steel, tearing through the ship's structural integrity before any internal partitions or reinforcing ribs can effectively impede its catastrophic advance. The structural disintegration of the SS Schenectady, upon retrospective analysis, presented an entirely logical sequence of events. Her construction had commenced in the nascent months of winter, employing welding methodologies that inadvertently amplified the inherent residual stresses within her metallic framework. Consequently, the vessel's hull harbored an immense burden of tens of millions of pounds of internal, constrained tension. As the dawn broke over Portland, bringing with it a precipitous drop in temperature to a frigid 28 degrees Fahrenheit, the ship's steel abruptly lost its pliability, transitioning into a dangerously brittle state. The severe localized stress at one of her cargo hatch corners provided the critical point for a crack to originate. This nascent fissure then discovered an unimpeded trajectory across the expanses of continuously joined deck plates. There were no traditional riveted seams present to act as natural impediments, nor any engineered stress relief mechanisms to halt its progress. The resultant fracture voraciously devoured the ship's integrity within mere seconds, unleashing an accumulation of decades of stored energetic potential in a singular, devastating structural collapse. Historically, vessels constructed using traditional riveting techniques were immune to this specific structural vulnerability, and the underlying rationale for their resilience cast a revealing light upon why the burgeoning technology of welding appeared to be afflicted by a perplexing curse. Riveted construction, by its very nature, embodies a discontinuous assembly principle. Each individual riveted plate functions as a distinct and independent structural component. Consequently, any nascent cracks that might originate within a single plate inevitably encounter a riveted seam and are effectively brought to a halt. The inherent design, featuring overlapping plates and robust mechanical fasteners, effectively establishes a network of natural barriers that arrest crack propagation. In stark contrast, modern welded ships are fundamentally continuous structures, presenting an unbroken pathway. A crack emerging in one section of plating can thus traverse unimpeded across hundreds of linear feet of interconnected welded seams. The very efficiency that rendered welded ships significantly faster to construct simultaneously rendered them susceptible to modes of failure that riveted ships simply could not experience. The Liberty ship's distinctive squared-off structural configuration further exacerbated this critical flaw. It was British maritime architects who had initially stipulated these rigid, angular corners, primarily to facilitate more straightforward and efficient cargo loading operations. Regrettably, no one at the time adequately considered that such sharply defined internal corners inherently generate severe stress concentrations, which possess the capacity to amplify applied loads by enormously significant factors. Each undulation of the ocean that caused the hull to flex sent intense spikes of stress directly through these vulnerable corners. When coupled with the already present residual stresses from the welding process and the material's susceptibility to brittleness, these geometrically problematic corners transformed into prime sites for crack initiation, patiently awaiting the precise confluence of environmental and operational conditions to precipitate a catastrophic structural failure. Henry Kaiser, a titan of industry, fully comprehended the profound implications that these scientific test results held for the colossal enterprise he had meticulously built and, more critically, for the overarching Allied war effort. In the pivotal month of January 1944, he took a monumental decision, one that would either decisively affirm the transformative power of his industrial revolution or irrevocably condemn him as an imprudent opportunist who had knowingly dispatched countless sailors to their peril aboard structurally compromised vessels. He issued an unequivocal directive for an immediate and comprehensive cessation of all Liberty ship manufacturing activities at his Richmond Yard 2 facility. Concurrently, he orchestrated the wholesale reallocation of invaluable resources towards the development and construction of a completely novel category of maritime transport, christened the Victory ship. This was no mere adjustment or incremental enhancement. Rather, it represented a foundational, wholesale architectural reimagining. Its core principles were meticulously informed by Bessie Hamill's groundbreaking observations regarding welding techniques, and the painfully acquired wisdom gleaned from the numerous fractured hulls strewn across the Atlantic and Pacific Oceans. The audacious wager undertaken by Kaiser was nothing short of breathtaking in its scope and potential repercussions. At this critical juncture, Liberty ships remained an absolutely vital necessity for the Allied war effort. German U-boats had, since the outbreak of hostilities in 1939, exacted a devastating toll, sinking in excess of 2,000 Allied merchant vessels. The impending invasion of Europe, still several months distant in the early part of 1944, was projected to demand an amphibious logistical undertaking of an unprecedented scale in recorded human history. Consequently, the contribution of every single ship was of paramount importance. Despite these overwhelming pressures, Kaiser was staking his entire reputation and fortune on the audacious premise that he could successfully integrate Hamill's innovative sequence welding methodology, fundamentally overhaul the hull design to eradicate dangerous stress concentrations, significantly enhance the metallurgical specifications of the steel, and remarkably, sustain manufacturing velocities that were already widely considered nothing short of miraculous. His industrial rivals openly questioned his sanity, convinced he had succumbed to an irrational delusion. Meanwhile, congressional investigators, poised and prepared, figuratively honed their instruments of scrutiny, ready to utterly condemn him should the ambitious production targets falter. Kaiser's highly skilled engineering teams adopted a reverse engineering approach, meticulously dissecting the identified points of structural vulnerability. Consequently, every single angular, rectilinear corner that characterized the original Liberty ship design was systematically supplanted by smooth, curvilinear transitions. The cargo hatch apertures, which had lamentably served as the origination points for a multitude of destructive cracks, underwent a comprehensive redesign, now featuring generously proportioned radii. This crucial modification effectively eradicated the perilous stress multipliers that possessed the capacity to transform routine operational loads into potent initiators of catastrophic fractures. Furthermore, the precise thicknesses of both the deck and hull plating were exhaustively recalculated, not with the primary objective of simply augmenting overall structural strength, but rather to guarantee an optimal distribution of stresses that harmonized seamlessly with the newly prescribed welding sequences. Even the fundamental arrangement of structural frames was reevaluated and strategically repositioned to inherently align with natural points of stress dissipation, thereby avoiding any counterproductive opposition to the intended welding pattern. Beyond the structural modifications, the very composition of the steel underwent a fundamental transformation. Kaiser's astute team of metallurgists meticulously formulated and specified an entirely novel alloy designation, specifically engineered to exhibit significantly enhanced toughness, particularly under frigid ambient conditions. This refined metallurgical blueprint involved a slight reduction in the carbon content, a constituent known to contribute to brittleness, while concurrently increasing the proportion of manganese, which imparts greater strength and ductility. Crucially, even minor incorporations of nickel, a metal then both prohibitively expensive and stringently rationed for critical applications like armor plating, were compellingly justified. This justification stemmed from empirical evidence demonstrating that a mere 0.25% nickel content dramatically augmented the steel's inherent resilience against brittle fracture. Initially, the Maritime Commission expressed considerable reluctance regarding the escalated costs associated with these advanced materials. However, their apprehension dissipated once Kaiser meticulously presented detailed economic calculations, vividly illustrating that preventing the loss of just a single ship due to structural failure would, in fact, offset the entire expense of the upgraded steel across an impressive fleet of 50 vessels. Consequently, in March 1944, the revised and superior steel specification received official sanction. Following the design and material innovations, an equally formidable challenge emerged: the colossal endeavor of fundamentally retraining the vast workforce. By early 1944, the sprawling Richmond shipyards alone accounted for an astonishing employment figure exceeding 90,000 individuals. Among these, Thousands were welders who had acquired their foundational skills through intensive, accelerated crash courses lasting merely a week, thereby mastering only the rudimentary techniques necessary to lay continuous, straight weld beads at the rapid pace demanded by wartime production. Now, however, these same individuals were suddenly required to grasp complex principles of welding sequencing, the intricate nuances of stress relief, and sophisticated thermal management protocols. In response to this urgent necessity, Kaiser proactively established dedicated welding schools directly within the confines of the shipyards. He strategically redeployed highly experienced and proficient welders, such as the insightful Hamel, from the production lines to serve as instructors. Each and every welder was issued a meticulously numbered sequence card for every distinct hull section, explicitly dictating the precise order of operations. Execute weld number 1 at this precise location, followed by weld number 2 at that specific point, ensuring absolute adherence to the prescribed, non-negotiable methodology. The existing prefabrication system underwent a profound and dramatic expansion. Instead of attempting to weld expansive sections directly upon the building ways, a method where maintaining precise sequencing proved exceedingly challenging, Kaiser's strategic planners ingeniously compartmentalized the Victory ships into significantly smaller, more manageable modules. These units were meticulously constructed within specialized, dedicated workshops. For instance, a single bow section might encompass as many as 50 distinct prefabricated subassemblies, each expertly welded under rigorously controlled environmental conditions utilizing optimal, predetermined sequences. Following this, these individual components were subjected to a crucial stress relief process within precisely calibrated heating ovens before their ultimate integration into the larger structure. This innovative modular methodology afforded welders the distinct advantage of commencing their work from the geometric center of each diminutive section and progressively working outwards, precisely as Hamel had empirically demonstrated, thereby liberating them from the inherent spatial and logistical constraints associated with constructing an entire hull in situ. The burgeoning cohort of skeptics found ample justification for their doubts when the keel of the inaugural Victory ship was ceremoniously laid in February 1944. Its construction spanned 18 days, a duration notably exceeding the record-breaking speeds achieved by the earlier Liberty vessels. It appeared, to many observers, that Kaiser's shipyards were no longer capable of manufacturing miracles. Rather, they were now merely producing ships at impressive, albeit not unprecedented, velocities. The subsequent second Victory ship, completed in 16 days, further fueled the critics, who promptly declared the entire program an unequivocal failure, positing it as incontrovertible evidence that superior quality and rapid production were fundamentally irreconcilable objectives. Yet, Kaiser, with unwavering resolve, chose to disregard these public pronouncements. His discerning focus was directed not primarily towards the raw construction timelines, but rather towards the meticulously compiled crack inspection reports. Crucially, the initial 2 Victory ships, upon thorough post-construction examination, revealed absolutely no evidence of stress cracks. This was not merely a reduction in crack incidents, but an astonishing, unequivocal absence of any such flaws whatsoever. By April 1944, the Richmond Yard 2 facility had undergone a profound metamorphosis, evolving into a meticulously orchestrated ballet of steel, intense heat, and synchronized human effort, a spectacle that would have been deemed utterly unattainable just 2 years prior. The physical layout and operational flow of the yard no longer bore resemblance to a conventional shipyard. Instead, it manifested as an immense, sophisticated assembly plant, characterized by discrete, specialized fabrication zones that continuously supplied components to a central assembly area where ship hulls rapidly coalesced with astonishing celerity. Kaiser had ingeniously adapted Henry Ford's revolutionary moving assembly line paradigm. However, in this maritime application, instead of the product traversing a linear path, highly specialized teams of workers systematically rotated through a series of fixed construction stations at precisely timed intervals. The meticulous construction process commenced within the expansive confines of the prefabrication sheds, colossal, sheltered edifices where welders diligently labored on hull sections, none of which exceeded 30 feet in any single dimension. Each of these precisely proportioned sections was accompanied by a dedicated, prescriptive sequence card. For instance, a single bottom plate assembly could necessitate as many as 47 distinct, individually numbered, and color-coded welds. Welders consistently initiated their work at position 1, invariably located at the exact geometric center of the section, and then systematically progressed outwards in either a meticulously planned spiral or a radial trajectory. Supervisors continuously patrolled the workshop floor, armed with comprehensive checklists, rigorously ensuring that no step in the prescribed order was inadvertently or deliberately bypassed. Crucially, following the completion of every 10 welds, the section was carefully transferred into a specialized stress relief oven, where it was uniformly heated to an intense 2,100 degrees Fahrenheit and subsequently allowed to cool at a meticulously controlled, gradual rate. This annealing process was vital, enabling the steel's intricate crystalline structure to undergo a crucial relaxation, thereby effectively dispersing any accumulated residual stresses before they could reach perilous, structurally compromising magnitudes. Furthermore, the raw steel materials themselves arrived at the shipyards in a state of advanced preparation, having been meticulously pre-cut and preformed directly from rolling mills that had undergone dedicated retooling specifically for the demands of Victory ship fabrication. This represented a significant departure from the practices employed for Liberty ships, where shipyard personnel were responsible for the laborious on-site cutting and shaping of individual plates. In stark contrast, all Victory ship components arrived entirely ready for immediate integration into the assembly process. Complex curved bow sections, for instance, were delivered perfectly preformed to their precise, engineered specifications. Similarly, deck plates featured pre-drilled bolt holes, facilitating swift and accurate temporary alignment. Even the intricate frame sections arrived as fully pre-welded subassemblies. This extensive preparatory work, meticulously executed within highly controlled factory environments, served to eliminate a multitude of potential variables and, consequently, guaranteed an unparalleled degree of consistency across tens of thousands of individual components. The final assembly process on the building ways diverged dramatically from the conventional sequence employed in Liberty ship construction. Rather than commencing with the keel and progressively constructing the vessel upwards in a linear fashion, Victory ships were assembled from large, prefabricated modules that converged and interlocked almost concurrently. The critical engine room section, the expansive cargo hold segments, along with the distinct bow and stern components, were all fabricated in parallel operations. These substantial units were then expertly lifted by colossal gantry cranes and precisely maneuvered into position during a singular, impeccably coordinated operation. On May 12, 1944, Yard 2 achieved its most audacious assembly feat to date, an astonishing 17 major modules, collectively constituting 85% of a complete hull, were accurately positioned and meticulously aligned in an extraordinary timeframe of merely 11 hours. Subsequently, welders meticulously joined these integrated modules, adhering to the identical center-outward sequencing protocols. However, a crucial distinction now applied. They were connecting sections that had already undergone comprehensive stress relief, rather than fabricating inherently stressed sections from their raw, nascent beginnings. The attainment of the rigorous 5-day construction timeline materialized through an unwavering dedication to maximizing the utility of every precious moment. Night shifts meticulously strategized and positioned necessary components and raw materials for the ensuing day shifts. Dedicated cadres of experts focused exclusively on scrutinizing structural alignment and the integrity of each weld, proactively intercepting potential flaws before they could metastasize into widespread issues. Precision-guided mobile cranes traverse predetermined pathways, ensuring the timely delivery of heavy structural elements to designated welding bays with an astonishing punctuality, often within narrow 5-minute time frames. Welders operated under a meticulously structured rotational system, 30 minutes of intense work with a torch followed by a 10-minute recuperation period. This regimen proved instrumental in sustaining an unblemished standard of quality, effectively mitigating the pervasive fatigue-related inaccuracies that frequently marred prolonged, arduous welding endeavors. Mr. Kaiser championed the adoption of his innovative critical path method, a sophisticated project management technique designed to precisely identify interdependent tasks, pinpointing those that constituted production bottlenecks and distinguishing them from activities capable of simultaneous execution. Should the installation of structural frames outpace projections while pipe fitting operations experienced a discernible lag, he promptly redeployed personnel, thus meticulously preserving an optimal equilibrium across every concurrent construction phase. Each instance of delay, every minute departure from the meticulously crafted timetable, was scrupulously recorded and subjected to rigorous analytical scrutiny. Daily morning convocations served as forums to meticulously review the preceding day's operational output, proactively isolating and resolving nascent challenges before their escalation into formidable, potentially catastrophic impediments. This extraordinary culmination of efficiency manifested on June 27, 1944, when the SS Benjamin Warner, designated as Victory Ship Hull No. 23, progressed from the initial keel laying to the completion of its demanding sea trials in an astounding 5 days and 11 hours. This achievement did not pertain to a mere stripped-down exhibition vessel, but rather to a comprehensively outfitted, battle-prime cargo carrier, replete with formidable defensive armaments, intricate and fully operational electrical networks, a robustly functioning engine room, and crucially, every single connection point, or more precisely, every weld, meticulously fabricated in strict adherence to the newly instituted stress relief methodologies. Remarkably, her robust hull exhibited an absolute absence of any fissures or cracks. Subsequent to her construction, a thorough inspection confirmed that all internal stress levels resided comfortably within the prescribed normal operational parameters. Upon embarking on her inaugural shakedown cruise, the Warner demonstrated impeccable performance, navigating with unwavering integrity even amidst environmental conditions that would have invariably compromised and fractured the structural integrity of earlier Liberty ships. The monumental success of the Victory Ship project transcended the mere attainment of accelerated construction schedules. Instead, it heralded a profound and comprehensive reevaluation of the entire paradigm for producing intricate machinery, particularly when sophisticated engineering principles were harmoniously integrated with the pragmatic exigencies of real-world construction environments. The pivotal observations made by Bessie Hamill had, in effect, initiated a cascading sequence of innovations, culminating in a systematic and revolutionary metamorphosis of the entire industrial shipbuilding landscape. The Victory-class vessels, meticulously crafted within Kaiser's extensively revamped and optimized production framework, represented an entirely distinct breed of maritime engineering when compared to their antecedent Liberty ships. While an untrained eye might perceive them as analogous cargo haulers fulfilling identical logistical imperatives, the profound disparities between the two classes originated at the most fundamental molecular level and permeated every conceivable facet of their design philosophy and actual construction. Whereas the Liberty ships had been conceived as urgent, temporary expedients to address a critical wartime exigency, the Victory ships stood as meticulously engineered solutions, specifically designed to systematically counteract every conceivable failure mode, many of which had been tragically illuminated by the ultimate sacrifice of countless mariners who had endured the harrowing experience of riding structurally compromised hulls into the unforgiving depths of the frigid Atlantic. The adoption of an enhanced steel specification emerged as an absolutely pivotal factor in this transformative endeavor. This novel metallurgical composition, formally identified as "killed steel," a designation derived from the deliberate introduction of aluminum during its manufacturing process to effectively deoxidize the molten metal, exhibited a profoundly superior resilience and toughness, particularly when exposed to frigid ambient temperatures. Exhaustive laboratory analyses unequivocally demonstrated that the crucial transition temperature, the precise thermal threshold at which steel undergoes a fundamental shift from a ductile, pliable state to a dangerously brittle disposition, had plummeted from approximately 40 degrees Fahrenheit, characteristic of Liberty ship steel, to a significantly lower value approaching 5 degrees Fahrenheit in the new alloy. Such a substantial 35-degree enhancement in thermal tolerance meant that Victory ships were capable of preserving their inherent structural pliancy and integrity even within environmental conditions that would invariably render Liberty ship hulls dangerously fragile and prone to catastrophic failure. While this superior material incurred a modest cost premium of 8% per ton, the resultant advantages in operational performance and safety were, by any metric, utterly immeasurable. Each minute structural element and design nuance meticulously incorporated into the Victory ships served as a direct testament to the profoundly advanced comprehension of stress concentration phenomena and the dynamics of crack propagation. Even seemingly insignificant modifications, such as the adoption of generously rounded hatch corners, which might appear to be a mere aesthetic refinement, were, in fact, engineered to diminish localized stress concentrations by a remarkable margin exceeding 60%. Rigorous engineering computations definitively illustrated that the abrupt, 90-degree corners characteristic of Liberty ship designs generated formidable stress multipliers, amplifying the nominal hull stress by factors ranging from 3.5 to a startling 4 times its original magnitude. Conversely, the Victory ships, thoughtfully integrated, ample radii successfully maintained these critical stress multipliers at a significantly safer level, consistently below 1.8. From a practical operational standpoint, this engineering superiority implied that a powerful wave impact, which would inevitably instigate the formation of a crack in a Liberty ship, would merely induce a momentary, resilient flexure within the Victory ship's hull, comfortably remaining within its inherent normal elastic limits. Furthermore, the very hull plates themselves were meticulously integrated with sophisticated crack arrestor features, ingeniously embedded directly within the vessels. Structural matrix. Departing from the practice of employing continuous welded seams that traverse hundreds of feet, Victory ships judiciously incorporated riveted seams positioned at precisely determined strategic intervals along their extensive hulls. These innovative hybrid connection points served as deliberate structural discontinuities, meticulously engineered locations where a rapidly propagating crack would inevitably encounter a robust mechanical joint, thereby experiencing a critical dissipation of its destructive energy, with the crucial potential of arresting its advance before it could catastrophically compromise the entire hull. The overarching design philosophy candidly acknowledged the intrinsic possibility of crack initiation, yet concurrently engineered a multifaceted array of arrest mechanisms specifically devised to preempt any catastrophic propagation. This approach epitomized a proactive, defensive engineering ethos, one that meticulously planned for potential failure modes rather than resting upon the perilous assumption of absolute perfection. To further bolster structural integrity, the critical stress points within the Victory ship's framework were reinforced with doubled structural frames, thereby ingeniously establishing redundant load paths. This intelligent redundancy ensured that, should a single frame exhibit signs of cracking or damage, its neighboring frames were fully capable of independently assuming and bearing the imposed loads until the vessel could safely reach port for necessary repairs. In stark contrast, Liberty ships possessed no comparable inherent structural redundancy. Consequently, a solitary frame failure in a Liberty ship frequently precipitated a cascading, progressive structural collapse, as the redistributed loads overwhelmed already compromised adjacent structures. The profound implication was that Victory ships possessed the remarkable capacity to endure damage that would unquestionably doom a Liberty ship, yet still retain operational capability, allowing them to courageously limp to port on structures that, while compromised, remained functionally intact. The precise welding sequences, meticulously derived from Bessie Hamill's groundbreaking observations, were rigorously codified into exhaustive procedural guidelines that meticulously dictated the execution of every single joint throughout the entire vessel. These comprehensive procedure manuals span hundreds of pages, not only delineating the exact sequence of welding operations, but also prescribing meticulous protocols for thermal management during the intervals between successive welds. Skilled welders underwent intensive training to assiduously monitor the interpass temperature, that is, the precise heat level of the base metal residing between consecutive weld passes. A strict directive mandated that if the steel's temperature surpassed 400 degrees Fahrenheit, all welding activities were to be immediately suspended, allowing the material to naturally cool to a safe operating temperature. This stringent control effectively precluded the detrimental cumulative heat buildup that had notoriously led to widespread, massive distortion during Liberty ship construction, a consequence of welders often working uninterruptedly on extensive seams, thereby superheating the steel into severely warped and internally stress-riddled configurations. The commitment to quality control escalated to an almost obsessive degree. Each completed weld was subjected to rigorous magnetic particle inspection, an advanced technique employing finely dispersed iron powder and precisely applied magnetic fields to expose even the most minute, subsurface cracks that would otherwise remain imperceptible to the naked eye. Furthermore, ultrasonic testing was deployed to meticulously verify internal weld quality, thereby guaranteeing absolute full penetration and the complete absence of any concealed voids or imperfections. For welds deemed critically important to the vessel's structural integrity, X-ray inspection was employed, generating permanent photographic documentation that irrefutably attested to the unblemished quality of each joint. No vessel was permitted to proceed to launch until authorized inspectors had meticulously certified that every single weld conformed impeccably to the stringent specifications. Initially, the rejection rate for welds was notably elevated. Indeed, close to 15% of welds on the inaugural Victory ships failed to pass the rigorous inspection protocols. However, the dedicated welders assimilated the new standards with remarkable alacrity. By the middle of 1944, the incidence of rejected welds had dramatically fallen to below 3%, an impressive achievement that served as a resounding testament to the efficacy of the comprehensive training programs, and the crystal-clear articulation of the newly implemented procedures. The ultimate validation of these innovative engineering and manufacturing philosophies unequivocally manifested during the ship's active operational service. From June 1944 until the cessation of hostilities in August 1945, an impressive fleet of 531 Victory ships were successfully commissioned and deployed. Crucially, not a single one of these vessels experienced a catastrophic hull failure, a stark departure from previous maritime experiences. While isolated, minor cracks did manifest in a small number of vessels. These were invariably identified as localized stress concentrations, promptly detected during routine inspections before they had any opportunity to propagate further. Such minor fissures were swiftly and effectively remedied utilizing the very same advanced stress relief welding procedures, allowing the ships to be promptly reinstated into active service. The demonstrable operational record presented an absolute and utterly damning contrast when compared to the performance of their Liberty ship predecessors. The stark human calculus, illustrating the profound disparity between the Victory ships and their Liberty counterparts, unfolded dramatically across two vast oceans throughout 1944 and 1945, indelibly etched in the countless lives preserved and the critical missions successfully brought to fruition, endeavors that, with earlier vessel designs, would have almost certainly culminated in unmitigated disaster. A poignant illustration of this resilience occurred when the SS Wanda Fuca, a distinguished Victory ship, tragically struck a naval mine off the coast of Okinawa in April 1945. The ensuing powerful explosion ripped a gaping 20-foot gash into her hull, perilously below the waterline. The ship's crew, well versed in the harrowing fate of previous vessels, braced themselves for the inevitable catastrophic crack propagation that had so frequently condemned Liberty ships to their watery graves. Yet, against grim expectations, the devastating fracture miraculously halted its advance at the very first strategically placed riveted crack arrestor seam. With remarkable fortitude, the Wanda Fuca managed to navigate to port under her own propulsion, underwent comprehensive repairs within a mere 6 days, and was promptly returned to active service. In a chillingly similar incident, the SS Richard Hovey, a Liberty ship sustaining virtually identical damage from a comparable mine strike in February 1945, experienced a catastrophic longitudinal fracture extending for over 90 feet, culminating in the breaking of her keel and her rapid descent beneath the waves in a mere 14 minutes, tragically claiming the lives of 37 crew members. The intricate and vast logistical demands of the Pacific campaign would have proven utterly insurmountable without the unparalleled reliability afforded by the Victory ships. As early as June 1944, American military forces were relentlessly advancing across the expansive Central Pacific, charting a course towards the strategic objectives of the Philippines and, ultimately, the Japanese home islands. Every successive island advance necessitated the monumental transportation of millions of tons of vital supplies, traversing thousands of miles of unforgiving ocean. While Liberty ships were technically capable of undertaking these arduous voyages, their inherent structural fragility unfortunately necessitated significantly reduced cargo capacities during tempestuous seas, imposed slower transit speeds to mitigate undue hull stress, and carried the ever-present, terrifying risk of catastrophic structural failure in vast, remote oceanic expanses far beyond the reach of timely rescue. In stark contrast, Victory ships routinely operated at their maximum design speed of 15 knots, a full 3 knots swifter than their Liberty predecessors, carrying their full complement of cargo through treacherous, typhoon-prone waters, entirely unburdened by the paralyzing apprehension that a combination of frigid nocturnal temperatures and violent seas might irrevocably cleave their hulls asunder. The empirical data unequivocally narrated the profound success. From the pivotal D-Day landings in June 1944 to the joyous declaration of VJ Day in August 1945, the Victory ship fleet successfully transported an astonishing volume exceeding 18 million tons of critical cargo, achieving this monumental feat with an impeccable record of 0 losses attributable to structural failure. These robust vessels routinely plied the perilous North Atlantic convoy routes, where ambient water temperatures frequently plunged below 35 degrees Fahrenheit, precisely the chilling conditions that had previously caused the catastrophic fracturing of dozens of Liberty ships. Moreover, they bravely navigated the formidable Arctic routes to Murmansk, diligently ferrying vital Lend-Lease supplies to the Soviet Union, traversing waters where near-freezing seawater temperatures had rendered Liberty ships terrifyingly susceptible to structural compromise. A notable example of this resilience is the SS Hobart Baker, a Victory ship, which successfully completed an astounding 17 Murmansk runs without developing even a solitary stress crack. Conversely, the Liberty ship John Walker, deployed on the identical demanding route, manifested critical cracks on only her second voyage, necessitating her permanent withdrawal from Arctic service. The permanent deployment of vessels in the Arctic brought forth a profound transformation in the morale of naval personnel, particularly as sailors transitioned from the notoriously fragile Liberty ships to the more robust Victory vessels. Post-war oral histories vividly recount the immense psychological burden endured by those who served aboard ships infamous for their propensity to spontaneously fracture. Merchant mariners frequently reported an omnipresent sense of anxiety, which was particularly acute in frigid conditions. Restful slumber became an elusive luxury, as every creak and groan emanating from the hull was perceived as a potential harbinger of an impending structural catastrophe. Consequently, some sailors actively sought transfers or outrightly declined to embark on specific Liberty ships known for their historical cracking issues. The introduction of Victory ships, however, instilled a renewed sense of confidence among crews. These vessels were relentlessly pushed to their limits, as their inherent resilience allowed them to withstand considerable abuse. This newfound assurance directly translated into enhanced mission effectiveness, significantly quicker turnaround times in port, a greater willingness to navigate in marginal weather conditions, and the execution of aggressive maneuvers when confronted with aerial assaults. The pivotal Battle of Leyte Gulf, which transpired in October 1944, served as a stark demonstration of the Victory ship's remarkable combat fortitude, enduring conditions that would have undoubtedly incapacitated Liberty vessels. A fleet of 16 Victory ships provided crucial support to the invasion force, diligently transporting vital ammunition, aviation fuel, and essential supplies while navigating through relentless kamikaze attacks and tumultuous typhoon conditions. The SS Kyle Johnson, for instance, sustained damage from a near-miss bomb, which resulted in buckled deck plates and fractures across 3 frame sections. Despite this significant damage, she steadfastly continued her operations, unloading cargo under fire for 4 grueling days, before finally withdrawing for necessary repairs. The inherent structural redundancy and meticulously engineered crack arrest features of the Victory ships were instrumental in preventing localized damage from escalating into catastrophic failure. In stark contrast, Liberty ships that experienced similar levels of damage typically had to be abandoned, as cracks rapidly propagated beyond any hope of control. The economic rationale underpinning this shift was undeniably harsh yet unequivocally clear. Each Liberty ship incurred an approximate construction cost of $2 million. Victory ships, on the other hand, demanded an investment of $2.6 million, rendering them 30% more expensive. However, Based on actual failure rates recorded up to 1944, a Liberty ship carried a 4.6% probability of experiencing catastrophic structural failure during its operational lifespan. Such incidents tragically claimed an average of 18 crew members per occurrence and resulted in the destruction of cargo valued at 3 to 5 times the ship's initial construction cost. The Victory ship's pristine record of 0 structural failures meant that the additional $600,000 construction cost was recouped within the first 6 months of service, solely through the elimination of inherent risks and a substantial reduction in insurance premiums. By the cessation of hostilities, merchant mariners had coined a grim yet poignant adage that succinctly encapsulated the fundamental disparity between the two vessel types. Liberty ships were built by the mile and cut off by the yard. Victory ships were built by the inch and measured by the year. These crucial inches, referring to the meticulous attention paid to welding sequences, the obsessive commitment to quality control, and the ingenious incorporation of engineered crack arresters, translated into decades of reliable service life, a stark contrast to the desperate prayers uttered every time the hull of a Liberty ship groaned ominously in the frigid seas. Bessie Hamill quietly transitioned back to civilian life in 1946, her return marked by an absence of fanfare or public acknowledgement, save for a commendation letter from her shipyard supervisor. She was never bestowed with a medal, never summoned to testify before Congress, and her name never graced the pages of the technical papers that subsequently chronicled the welding revolution she had initiated. The established engineering community readily absorbed her groundbreaking insights, meticulously repackaging them in abstract mathematical language and arcane academic terminology. These discoveries were then published as if they had originated from rigorous laboratory research rather than from the astute practical observations of a night shift welder. For many decades, welding textbooks diligently imparted the principles of stress relief sequencing without ever acknowledging the woman who had first recognized its critical necessity while witnessing hull plates distort under the intense heat of her torch. Nevertheless, Hamill's enduring legacy profoundly permeates modern engineering, extending its influence far beyond the confines of shipbuilding. Every welded structure erected today, from towering skyscrapers to vast pipeline networks and robust pressure vessels, meticulously adheres to sequencing protocols directly derived from the procedures meticulously developed at Richmond Shipyard in 1944. The American Welding Society's Structural Welding Code, first promulgated in 1947, formally codified center outward welding sequences and stringent stress relief requirements as mandatory industry standards. The ambitious construction of pipelines across Alaska in the 1970s heavily relied upon welding procedures that explicitly reference Victory ship methodologies to effectively mitigate cold weather cracking in the harsh Arctic environment. The very existence of the Trans-Alaska Pipeline, with its 800 miles of welded steel efficiently transporting hot oil through sub-zero temperatures, stands as a testament to engineers' comprehensive understanding of the invaluable lessons imparted by Hamill. Modern bridge construction has similarly inherited and embraced these fundamental principles. The catastrophic collapse of the Point Pleasant Bridge in West Virginia in December 1967, which tragically claimed 46 lives, identified residual welding stress as a significant contributing factor. The subsequent investigation meticulously revealed that welds executed without proper sequencing had inadvertently locked dangerous stress concentrations into critical structural members. In the aftermath of this disaster, comprehensive code revisions were implemented, mandating the sequencing and inspection protocols that Victory ships had pioneered. Consequently, every welded bridge constructed since incorporates these essential requirements. The extensive seismic retrofit of the Golden Gate Bridge in the 1990s, which involved the addition of thousands of tons of welded steel reinforcement, employed sophisticated computer-modeled welding sequences meticulously optimized to minimize residual stress. Advanced iterations of the techniques Hamel had so effectively demonstrated with hand-welded test plates back in 1943. The offshore oil industry has repeatedly learned this crucial lesson, frequently at considerable expense. The devastating Alexander Kielland platform disaster in Norway in 1980, which resulted in the tragic deaths of 123 workers when the platform capsized, was partially traced to fatigue cracks propagating from improperly sequenced welds. The catastrophic Piper Alpha platform explosion in 1988, claiming the lives of 167 men, originated from a crack in a welded pipe connection that had accumulated significant residual stress. Each of these calamities prompted investigators to meticulously scrutinize welding procedures, and each subsequent investigation invariably rediscovered the very principles that Victory ship construction had conclusively proven 4 decades earlier. Contemporary offshore standards now stringently mandate stress relief heat treatment for all critical welds, a direct echo of the massive ovens Kaiser had installed in Richmond's prefabrication shops. Nuclear pressure vessels, which meticulously encase reactor cores under extreme temperatures and pressures, represent the ultimate embodiment of stress relief welding applications. The colossal steel shells designed to contain nuclear reactions cannot tolerate even the slightest initiation points for cracks. Welding sequences for these vital reactor vessels are meticulously planned with computational precision, carefully simulating thermal effects and residual stresses even before the initial weld is struck. The entire vessel then undergoes post-weld heat treatment in enormous ovens, precisely mirroring the process applied to Victory ship sections, thereby effectively eliminating any residual stresses that could potentially evolve into failure initiation points. The engineers responsible for designing these intricate procedures in the 1950s explicitly studied Victory ship construction as their foundational reference point. Hamel's astute observation fundamentally reshaped how engineers conceptualize fabrication processes. Prior to the advent of Victory ships, design and construction were largely disparate domains. Engineers meticulously designed structures, while fabricators meticulously built them, with minimal communication between the two groups regarding how construction methodologies impacted structural performance. Victory ships unequivocally demonstrated that the fabrication sequence was as critically important as material selection or the structural design itself. Modern engineering education now integrates manufacturing processes as indispensable components of design courses. Engineering students are now taught that an impeccably conceived design, if executed with a flawed fabrication sequence, will inevitably yield inferior results compared to a more modest design constructed with proper procedures. The impressive 5-day construction timeline, while certainly remarkable, was never the true measure of achievement. Kaiser's shipyards possessed the capability to sustain Liberty ship construction speeds indefinitely, continuously launching defective vessels that appeared seaworthy until their inevitable fractures. The actual marvel resided in the courage to deliberately slow down sufficiently to execute the work correctly. It was the audacious willingness to halt production and fundamentally redesign processes based on a welder's insightful observation that directly contradicted established practices. This profound willingness to actively listen to frontline workers, to humbly acknowledge that prevailing engineering theory had overlooked a crucial element, and to comprehensively redesign systems around observed reality rather than stubbornly defended assumptions. That, indeed, was the true revolution. Every modern manufacturing methodology, from Six Sigma to lean production to total quality management, intrinsically embeds this foundational principle. The worker, intimately observing the intricacies of the process, frequently discerns critical details that an engineer calculating from a remote desk simply cannot perceive. Bessie Hamill passed away in 1987 in Sacramento, her obituary merely noting her wartime employment in shipyards. Yet, every welded structure standing proudly today, every pipeline traversing frozen landscapes, every pressure vessel containing perilous forces, every bridge gracefully spanning rivers, all of them carry her indelible legacy within their meticulously sequenced welds and expertly stress-relief joints. They stand as silent, enduring testaments to the pioneering welder who dared to question why ships were breaking apart and steadfastly refused to accept "that's how it's done" as an adequate explanation.